Welcome back to the next video, everybody. We are going on to chapter 8 of my notes, where we will be covering an introduction to deformation theory of Galwa representations. So let's get into this. Let's let K be a field, and let's let K bar denote a choice of separable closure of K. We'll let G sub K denote the absolute Galwa group of K, so that's the Galwa group of K bar over K. We know that GK is a profinite topological group under the Kroll topology, where a basis of open neighborhoods of the identity is given by those which fix finite extensions of K and K bar. So we talked about this in chapter 1. Now let's let K be a number field specifically, and we'll let S be a finite set of non-Archimedean places of K, that is of non-zero prime ideals in the ring of integers of K, OK. Then GKS will denote the Galwa group of K bar S, which is the maximal algebraic extension of K in K bar that's unramified outside S. Okay. Equivalently, by basic algebraic number theory, this field is the union of all finite extensions of K and K bar whose discriminant is not divisible by a prime outside of S. Okay. So here's the problem. Here's what we want to do. If we fix such an S and a number D, let's say, then the Hermite-Minkowski theorem says that there are only finitely many field extensions of K and K bar of degree at most D unramified outside S. However, the problem here is that K bar S over K is often of infinite degree. That is, GKS is often an infinite group. For example, take the case where S contains all the primes of K lying above a certain fixed prime in the rational prime. The profinite group GKS with its Kroll topology is a natural quotient of GK. The kernel of the projection from GK to this quotient is the closed normal subgroup generated by all inertia subgroups of GK by definition of inertia subgroup attached to the places V and S. Remember, inertia is where we act residually trivially. So that's exactly means we're in the kernel of this projection. Okay, so GK is countably infinitely generated as a topological group, which is sort of a problem, right? It's hard to get a handle on GKS even. Forget GK. We don't even know whether it's finitely generated as a topological group, believe it or not. It's actually known that GKS, though, has the following helpful property called p-finiteness. Let's let P be prime and let's let pi be a profinite group. We'll say pi satisfies the p-finiteness condition, which I'll call PFC. If for all open subgroups pi 0 inside pi of finite index, there are only finitely many continuous homomorphisms from pi 0 to Z mod PZ. You can see Mazur's deformation theory, kind of his main paper on the subject, for more details about this definition and equivalent formulations. Okay. For example, pi equals GKS satisfies p-finiteness for all primes P. Indeed, if I give you any open subgroup pi 0 and pi of finite index, it itself is of the form G K0 S0 for some finite extension K0 over K and for some set S0. So by the universal property of abelianizations of topological groups, the continuous maps from this GK0 S0 to Z mod PZ are the same as the continuous maps from the abelianization of GK0 S0 to Z mod PZ. And this latter set is easily shown to be finite via class field theory. Okay, what is abelianization here? The abelianization of a profinite topological group is the maximal profinite topological quotient group, which is abelian. So take the quotient by the closure of the commutator subgroup, and you get your abelianization. Okay, so it's like, all right, what are we supposed to do if we can't get a handle on these GKSs? Well, let's instead consider the following setup. So for each place V of K, a choice of embedding K bar into K bar sub V, where K sub V is completion at V, gives a continuous homomorphism IV from GKV to GKS. Okay, so GKV here is the Galwa group of K bar V over KV. If I change the embedding, that changes IV by conjugation, so no big deal. If V is non-Archimedean and not in S, then IV will factor through the quotient of GKV by the inertia subgroup IKV, right? By definition of inertia, giving a homomorphism I, which we'll still call IV, from GKV mod inertia to GKS. Now, the former group is canonically isomorphic to G sub little k sub V, where little k sub V is the residue field at V. Little k bar sub V is the residue field of the valuation ring of K bar sub V. Now, G little k sub V has a canonical topological generator P sub V, the Frobenius element that sends X to the cardinality of little k sub V. Okay. And then you can pull this generator back here to this quotient and take representatives in G big K sub V called Frobenius elements. We talked about this in chapter 1 again. Okay. The map I sub V is determined by the image of one of these Frobenius elements, which we'll still call V sub V. Okay. So these, once you mod out by inertia, these maps are always determined by where they send Frobenius elements. That's the key. All right. We recall that the Frobenius element is unique only up to conjugation. Okay, basically because we have a choice of embedding going on here. And we will refer to this image as the Frobenius element Frob V in GKS attached to V. So take a Frobenius in this Galwa group here, pull it back to a representative here, and then take its image here. That's still going to be called a Frobenius at V. We'll call it Frob sub V. Okay. If V is real, the local Galwa group G sub K sub V is cyclic of order 2, and the Frobenius element there will refer to the image of just the non-trivial element of G sub K sub V. Okay. So the goal is to study the isomorphism classes of the entire package GKS and the conjugacy classes of the homomorphisms IB from local Galwa groups of V into GKS for all places V of K, instead of just trying to study GKS itself. Equivalently, we seek to understand the package consisting of GKS, the conjugacy classes of the Frobenius elements at V in GKS for all places V of K not an S, and the homomorphisms IB from GKV to GKS for the finite set of places V and S. Okay, so you don't just study GKS, you study these kind of local maps into it as well. This approach is much more fruitful because, for example, the GKVs are topologically finitely generated, unlike the GKSs in the GK. Okay, another approach that you might take is we even know quite a bit about the abelianization of GKS, and in fact, about the abelianization of this entire package up here. This is exactly the study of class field theory in some sense. Okay, so again, I like Milne's notes for class field theory. There's also Sayre's books. All right, so what happens when K is Q? When that happens, the situation is very well understood. Let S be a finite set of prime numbers. Let mu sub S denote the nth roots of unity in Q bar as n ranges throughout all numbers whose set of prime divisors is contained in S. The Kronecker-Weber theorem says, Kronecker-Weber theorem, excuse me, says that the maximal abelian extension of Q unramified outside S is exactly the subfield of Q bar generated by mu sub S. And then we have canonical isomorphisms from the abelianization of GQS to the Galwa group of Q adjoin mu S over Q, to the automorphisms of mu S, to the product over P and S of ZP cross, where ZP is the p-adic integers. What's the Frobenius element at any prime L not an S? That corresponds under this isomorphism to the element here in this product, whose p coordinate is given by the integer L and ZP cross for each P and S. Okay? So it's like complete and total understanding of the situation as expected when K is Q. So here's the question, can we go beyond the abelianization of GKS? Well, the problem is that GK is not only non-abelian, it's defined up to choice of K bar, so it's only defined up to conjugation. So it's like, all right, so what do you do then? Well, you do what you always do in these kinds of situations. You study GK in terms of its representations up to isomorphism instead. Maybe you can get a handle on it by looking at its representations. Okay? And one reason this is particularly powerful is that this approach doesn't care that GK is only defined up to conjugation. Okay? So from this point of view, class field theory provides an essentially complete theory of the one-dimensional complex representations of GKS. All right. So enter Galois representations. If we want to try to push further, we should naturally consider what we call Galois representations, continuous homomorphisms rho from GKS into GLN of A, where n is some natural number and A is some topological ring. We'll say which topological rings next time. By the above discussion, what we actually want to do is understand such representations in addition to their restrictions to the Galwa groups G sub K sub V for all places V of K, i.e. what we call the local representations at each place V of K. Okay, so if V is a place of K that's not an S, the restriction of rho to GKV is understood, as we talked about, simply by knowing the conjugacy class of the image of rho of phi sub V of the Frobenius phi sub V. It turns out really though that all you really need to get a handle on is the trace AV of the image of rho of phi sub V. This is independent of the choice of Frobenius because it's independent of rho up to conjugation, because trace is conjugation invariant. So it's a well-defined invariant of the equivalence class of rho if V isn't an S. So that's great. We don't really need to understand the image of phi sub V entirely as much as just its trace. We'll see that in many cases, the data that maps V to A sub V for V not an S is actually enough to recover rho up to equivalence. In fact, we have the Chebytarov density theorem, which says that often we need even less, just that same data for V ranging even through just a set of places of density 1 outside S. You don't even need to understand this data for all places V outside S. So here's the theorem. If F over Q is a Galois extension unramified outside of finite set S of primes, then the union of the conjugacy classes of the Frobenius set P for P naught and S is dense in the Galwa group of F over Q. Okay, so for a proof, you might see Milne's class field theory. All right, so next time we'll start looking more carefully at which rings that we want to look at here when we're looking at Galwa representations. So I'll see you then, and thanks for watching.